Hello. So today we will start our recording for the paper 2 and we'll see what is in there for us to answer the questions. So this is the paper which is the paper of 22nd of May 2018. Now we will try to answer the questions uh, in this paper. Moving on without any further ado towards the questions, what we have in here as the first question is to identify the group in the periodic table which has the most reactive metals elements, and they turn out to be metals. Okay, so the group on the extreme left in the periodic table has the elements and they are metals, and they are the most reactive metals of all in the periodic table, and they are called alkali metals. So the group name turns out to be the group of alkali metals group, which is the most reactive group of metals in the periodic table. So that's the answer for the second question, which is basically a part, a part A of the first question, and it is the second part of the sub question A, which is in turn a part of the whole question, which is number one, and which says the group that contains colored nonmetals. Till yet, I didn't find any concrete answer to this question, so that's why I have for the time being left it blank, and I'll try my search to find answers to this question, and as soon as I find it I will write it in here. So for the time being we keep it as it is, and then we move towards the next question, which is asking us to name the group of the elements of the periodic table that are the least reactive. So the group which is on the other extreme of the periodic table than the alkali metals group is the group which we call the group of noble gases. And by the name noble gases, what it means is they are so noble that they don't try to react or intermingle with other elements of the periodic table. So they are so inert or isolated that they don't want to form compounds uh, involve in some sort of bonding with other elements of the periodic table. So that's why they are referred to as the least reactive elements in the periodic table, and they are the noble gases of the periodic table. So that's why the group is called the group of noble gases of the periodic table, which is the least reactive group in the whole periodic table. Okay, so now we come towards the question, uh, subsection B of question number one, which asks us to write the number of neutrons that are in the element polonium. The straightforward answer is 125. There is no that much of a discussion in this question because it's just a straightforward number, and this number represents the number of neutrons. Neutrons are basically one of the nucleons of any element, the other being protons. So this is one of the heavy elements in the periodic table. That's why it has so many neutrons, and also it has a lot of protons. It is one of the heavier elements in the periodic table. Okay, so that's why you see such a large number 125 for its number of neutrons. Okay, also for the next question, part second of subsection B, I didn't manage to find a reasonable answer for this question. Maybe I don't understand this question in the right sense. That's why I was not able to have a concrete understanding of this question. And for the time being, I have left it as it is as well. This is the second one. I think there are only two questions that I have left like that in the whole uh, paper 2. So after I finish delivering this lesson for today, I will try to continue my search and look for some reasonable answer to uh, these two unfilled blanks rather, and I will try to fill them as soon as I find the relevant answers. Okay, so for the time being, we also would like to continue to the third part of this subsection B, which is asking us to write the valency of the zinc element. So, well, the valency is basically the number of electrons in the outermost shell of any element. So in the case of zinc, it turns out to be two, which are responsible for zinc to make it bond with some other elements and form compounds. So these are the players, you can say, that come into action and allow for zinc to make compounds by forming bonds with other elements of the periodic table. So it is in this case of zinc, there are two. So that's what we have written in here. Okay, let me just check if we are fine with our recording or not. Okay, so the recording is carrying on. All right. So the next thing is this is the part 4 of subsection B, and the question says name the element whose iron turns brick red in a flame. Okay, so this is talking about the flame test. There are certain elements in the periodic table which, when are put to flame, they give specific colors to the flame that are characteristic of those particular elements. So this flame test is basically a method to identify which are those elements, because some specific elements give characteristic colors to the flame. So, for example, if a particular element is known to give some color A to the flame, then it readily gets identified that this is the unknown element is this one. So, as in the case here, if some unknown element gives the flame the particular brick red color, then it readily gets identified as calcium. So maybe then the sodium could give some other specific color, so as the case can be in the for potassium or other elements, for example. So but for calcium, the characteristic color is brick red that it gives to the flame when it is put with the flame, put in the flame test. Okay, so this is for it. Now we come to the subsection C, and the first question in the subsection B is asking us to create or construct a bond diagram for the compound ammonia. As you can see, ammonia as a compound that is made up of nitrogen and hydrogen elements. So, in the case of ammonia, one nitrogen atom is combined with and or forms bond with three hydrogen atoms, and the product turns out to be ammonia. So what nitrogen has is the valency of nitrogen is 5 because it has 7 electrons, and the valence electrons are 5 out of those 7 that nitrogen has in total. So uh, the way it works in forming bond is it gets attached to itself 3 hydrogen atoms, and those 3 hydrogen atoms, each hydrogen atom has only one electron, and that also is valence electron. So it has only one shell, and that too is unfilled, because the first shell of any element has to have at least 2 electrons to be regarded as a full or completed shell. But in the case of hydrogen, this only one shell is also unfilled. So it, in order to attain stability, it wants to form pairs with some other unpaired electrons from some different elements. So in the attempt of doing so, 3 hydrogen atoms try to make pairs with 3 electrons from nitrogen, and in doing so, they, as you can see in here, these small uh, red these small blue circles are representing ammonia. No, sorry, these small red blue circles are representing hydrogen atoms, and this bigger red circle is representing nitrogen. So, if you can see these tiny dots in colors of green and red, so this green is are representing the electrons, the valence electrons of nitrogen, and these red dots are representing the only electrons of each hydrogen atom. So as you can see, this red electron of hydrogen is making a pair with a green electron from nitrogen. Same is the case here and here as well. So you can see all of the unpaired ones form pairs, and these two electrons already had pairs, so they don't need to make any bonds with any other unpaired electron. So this is the bonding diagram of ammonia, in which you have one nitrogen atom and three atoms of hydrogen. This is how it is. So this is the answer, or rather detailed answer I can say, for this question. And then moving on further, we have been asked to give one use of ammonia, and the most one of the most common, I can say, use utilization of ammonia is in fertilizing, or in other words, we can say that it is being used as a fertilizer, as a common use case. So this can be one good example right in here, as one of its main uses, that it is this ammonia compound is used as a fertilizer in the agricultural industry, or in the agricultural sector. Okay, moving on further, what we have in here is, we have now the second question, the question 2. This all was the first question, and there are so many parts to the first question. Now only we have moved to the second question after answering all those ones before. And the first question, the first thing that is being presented to us is a lattice structure. This that you can see, this cube form that you can see, is called a lattice structure in the lingo of chemistry. And there you see the atoms of chlorine and calcium together, arranged in some specific order to form the calcium chloride compound. Okay, and after given this representation of the lattice structure of calcium chloride, we have been asked some questions related to it. And the first question, uh, of the subsection A, and then the first part of the subsection, is asking us to describe the movement and spacing of the particles that make up this lattice. As I told you, this representation is called a lattice, in which you have specific edges, and you can see some atoms sitting at those edges, and in the body, throughout in the body, at some particular locations in the lattice. So we have been asked to describe the movement and spacing of the particles that make up this lattice. So what we can say here as answering, at answering this question, is that at the edges, as I told you, these are the edges. You can see these corners, at the edges, and at the center, at the very center. You can see that at the edges and the center, the circles are smaller. Elsewhere, they are bigger. So, so the smaller ones are representing calcium ions, and the bigger ones are representing chlorine ions. So these bigger ones that you can see my cursor here. This one is for chlorine ion. This also is chlorine, chlorine, this chlorine, this chlorine, this chlorine, and the rest, including all at the edges and at the center, are calcium ions. So this is how they are arranged in this fashion here. in making up the calcium chloride compound. Okay, and now moving on to the second question of the subsection A. Uh, we have been with one we have been given with one example usage of calcium chloride, and that is to melt ice. Let me check again if the recorder is working properly. Yes. So the question says that we need to explain the effect that the calcium chloride has on the melting point of ice inside the new melting point. So since calcium chloride is used as a compound to melt ice, so now what is the underlying process it that it undergoes to melt ice? So there's the crux of this question. So what happens is, the reactions are of two types basically: exothermic and endothermic, depending on if they are releasing the heat or they're absorbing a heat in order to go through the process of having a reaction. So the compounds can either be, or the process, you can say the process involving certain compounds can either be exothermic or endothermic. If the heat is being released as a result of of the process, some specific process, then the reaction is called an exothermic reaction. But if the heat is being supplied to the reactants to undergo the process and then produce some products, so if the heat is supplied, it means that the heat is being absorbed by the reactants so as to be able to react together and make some products, then that reaction is called endothermic reaction. So the case here is calcium chloride goes through exothermic reaction process, and in doing so it releases heat, and this heat is used up in melting ice. The heat that the calcium chloride generates or releases uh, by virtue of going through some chemical process is used up is in melting ice. Okay, because calcium chloride reacts with the moisture in the air, and when it reacts with the moisture in the air, then it releases heat, and this reaction allows calcium chloride to release heat, and this heat then makes the ice to melt when it's applied to ice. Okay, all right. Now we have moved to subsection B and then to part 1 of the subsection. We have been asked to write the electronic configuration for calcium and chlorine both. So first, for calcium, since we know that calcium has 20 electrons because it has also 20 protons, so in order to be electrically neutral, the positively charged protons have the negatively charged electrons in same amount or same number as well. Only then it can be electrically neutral or stable. So this calcium has 20 protons, so it has to have 20 electrons. So those 20 electrons are distributed in some orbits or shells. How they are distributed? So we can see this is 1s2, which meaning that the first shell has two electrons, and it can have only two electrons at most. So this is what it is. Moving on, we have the second shell. In the second shell, at most 8 electrons can reside. So this is shown to us by 2s2 2p6. We can see that this is a 2s is representing the second shell, and also 2p. So 2s2 meaning 2 electrons, 2p6 meaning 6 electrons. 2 plus 6 is 8. So this 2s2 2p6 is telling us about the second shell, which is telling us about the 8 electron in the second shell. After filling the second shell with 8 electrons, we now move towards third shell, and this third shell has again 8 electrons. In the third shell, by the way, it's the possibility to have 18 at most electrons, but because uh, we are running out of electrons when we are talking about calcium, because when we have moved from first, second to third, we already have counted uh, 10 electrons when we reach the third one. So we don't have 18 more, because we only need 10 more when we have counted up till 10 already. When we have moved, by the time when we have moved till third one, we only have 10 more electrons to accommodate in shells. So that's why we can fill third electron not with 18 but with only 8 electrons, and then we will move towards the fourth shell. Why we are moving towards fourth shell? It is due to the requirement of stability for the um, uh, element or metal, whatever the case may be. So if we keep on increasing the number of electron, or we keep on moving towards more and more heavier elements in the periodic table, this is what we start to see, that before even the third shell is fulfilled or filled with 18 electrons, a fourth one kicks in when we write this electronic configuration. So this is how the case is also here for calcium. So we have this 2 plus 2 plus 6 10 electrons, and then we have 2 plus 6 plus 2 plus 10 more. So this is how we write the 20 electrons when we talk about electronic configuration of calcium. So this is the electronic configuration for calcium to accommodate its 20 electrons. Now for chlorine we have 17 total electrons. So this is how we write for chlorine. So again the same thing for chlorine, for 1s2 2s2. Okay. Also for 2p6 is same as is what the case with calcium. Then we have again the same thing till here 3s2. Yeah, here we run out of electrons, because by the time we do 3p5, we already have counted for 17 electrons for chlorine. So this is how we write the electronic configuration in the case of chlorine. So if we count 2 plus 2 plus 6 10 plus 2 12 plus 5 17. So we have represented all the 17 electrons this way for chlorine. This is the electronic configuration for chlorine, because chlorine has 7 protons, 17 protons and 17 electrons. Okay, which is 3 less than calcium, by the way. All right, now we move towards the second part of subsection B. So we have been asked to write the bonding that calcium and chlorine have when they form the compound calcium chloride. So it's ionic bonding. So there are certain types of bonding depending on between which elements this bond, the specific bond is being formed. So sometimes it's covalent, sometimes it's ionic, sometimes it's metallic. All right, but in the case of calcium chloride, it's ionic bonding, because one of the elements here is more electronegative than the other. So when there is a significant difference between the electronegativities of elements taking part in bond formation, then the bonding result is ionic bonding in those cases. Okay, so this is the case here, and we move on towards part 3 of subsection B. We have been asked to draw the Lewis dot bonding diagram of calcium chloride using only outer shell electrons. So Lewis dot bonding diagram asks us to uh, as in as in is in the name dot bonding diagram. So we have to represent the valence electrons as dots. Okay, and we have to use the arrow in order to signify or represent the uh, uh, the inclination of the electrons towards specific elements. So in the case here, as we saw in the electronic configuration in the last question, so for the case of calcium, the valence electrons are 2, and for the case of for the case of chlorine, this, there are seven, I guess. Yes. Okay. So that's what we have done here. We have represented the valence electrons of chlorine by pink dots and the uh, valence electrons of calcium by tiny blue dots, if you can see here. So these arrows represent that on either side of the calcium, that since the electronegativity of chlorine is more than the electronegativity of calcium, that's why it attracts the calcium electrons towards itself. But also it wants to complete its octet. So because chlorine already has seven valence electrons, only needed one to complete its octet and be stable. That's why this is a stable configuration when the compound calcium chloride forms between calcium and chlorine. These two valence electrons of calcium are, uh, you can say, pulled by the chlorine uh, ions on either side to attain their stabilities. So this is how it works here. You can see on the either side of the calcium, these arrows, which is representing the process of pulling of those electrons in forming the ionic bonding between calcium and chlorine ions. Okay. Okay, then we will move towards section of part 4 of subsection B, I guess. Yes. And the question asking us to explain why calcium chloride conducts electricity when it is molten or dissolved in water. So the answer to this question is calcium chloride has the property that it gets dissolved in water. Okay. And when it does so, it gets separated into their, I mean, its respective ions. This compound gets separated into its building blocks because of the constituent ions. Okay. So because it does so, it is classified as a strong electrolyte. Because in electrolyte we need to have ions. If there are no ions in the electrolyte, then the electrolyte is not an electrolyte in true sense. Because electrolyte at last has to conduct or support electricity conduction, and this only is possible through the presence of ions. So when calcium chloride breaks into ions, it is working as a good electrolyte because it then supports electrical conduction through itself. Okay, so that's why you can read here the line that says that when dissolved in water, it is able to conduct electricity because it is broken now after solution, so getting dissolved in water into its respective ions. So when it is broken up into its respective ions, then it can assist the flow of electricity to it and hence work as a good electrolyte. Okay, so this is, hope the answer to the question is well understood here. And let me check again if the it's working. Okay, and then moving on to question number 3. Alkalis and acids can be prepared by dissolving peroxide in water. Okay, now we have given with 4 oxides, or maybe 5, yes, 5 oxides, and the question asks us to uh, answer the question of subsection A, and the part 1 of subsection A is asking us to name 2 of the oxide of the from the list of 5 and the acid that they form. And when do they do this? They do this when they react with water. These oxides, there are two oxides in the list of five. When they react with water, they form acids, and these are the last two. And the sulfur dioxide, if the sulfur dioxide reacts with water, it forms sulfurous acid. And the very last one is sulfur trioxide. This sulfur trioxide, when reacts with water, it forms sulfuric acid. So one of them, the second last, when reacts with water, it forms sulfurous acid, and the fifth one, the sulfur trioxide, when it reacts with water, it forms sulfuric acid. So these are the two that when react with water, they form uh, their respective acidic counterparts. Okay. Now moving on to part two of subsection A. So again, it is referring to the list of five and asking us to uh, write two of the oxides that form soluble base. So by soluble they mean water soluble bases. Okay, bases that don't result in precipitation when they are put into water. Okay, so these are the sodium oxide and potassium oxide. As you can see in the list as well, you will find sodium and potassium oxide here. So these are the two oxides that when are put into water, they are soluble and they form soluble bases, result in no precipitation, and the product is formed as a base. And in the case of sodium oxide, this is a sodium hydroxide, a very popular base. And in the case of potassium oxide, it's a potassium hydroxide base. Okay, sorry. And then we will move to part 3 of subsection A of question 3. It is asking us to, okay, so basically some of the chemicals are classified as acids, some are bases. So another word you can say, maybe a synonymous classification for bases, is alkalis. They can also be referred to as alkalis or alkalis in some parts of the world as people refer to it. So soluble bases are also classified as alkalis. This is what it asks us to give the terminology here for the chemical classification of soluble bases. And then question 4 is asking us to using an acid from a one and one soluble base from a to write a word equation. Okay, so a1 is the part. And okay, so basically what it is asking us to name the reaction when we classify particular reactions. What are they called when the reactant, one of the reactants is an acid and the other is a base? Okay, so this basically is a neutralization reaction that we call it. So when the acid and base react together, they form compounds, and this process is called neutralization or the neutralization reaction. Okay, now we have moved to subsection B. In the part 1 of subsection B is asking us to tell the color of litmus paper uh, when it is put in hydrogen chloride gas, HCl gaseous form. HCl can be in liquid form as well, but here is the case of HCl, hydrochloric acid, a very, or hydrogen chloride is it is referred here as a it's a compound in gaseous form. So what should be the color of the damp blue litmus when it is placed in this particular gas? So the answer is the color does not change at all because hydrogen chloride gas does not release ions. So if it's gaseous, the environment does not have any moisture, and this hydrogen chloride gas is not the same as hydrochloric acid, because it is hydrochloric acid that releases ions and that turns the color of litmus to something else from something else. So here it remains in its original color. So when it is damp blue, it will stay damp blue because there is no release of ions in the absence of moisture in the case of hydrogen chloride gas. Okay, this hydrogen and chlorine, when uh, in acidic form, this compound, then it changes the color only. Okay, now towards part 2 of subsection B, let me check again how many minutes have elapsed in recording this. Okay, 31 minutes. uh, we have been asked to name the alkaline gas that reacts with hydrogen chloride to produce thick white smoke. Okay, so it's ammonia. This ammonia is a gas just which when reacts with hydrogen chloride, it produces the thick smoke. This is the characteristic of ammonia, and it's classified as an alkaline gas. All right, and then also a related question follows. Uh, this thick white smoke has a certain name, and this is ammonium chloride. Uh, this the chemical name of this compound. Okay. Now moving on towards the next question, question number 4. We have been shown with a blast furnace diagram. Here we see various levels with different temperatures at each level, and some inlets and some outlets here down the diagram, and also up the diagram there are some points from where something is coming out, some point where something is coming in. And now we, after this diagram, see some related questions. And the subsection A, part 1, asks us to refer to the diagram and tell the names of the material leaving the blast furnace at X and Y labels in the diagram. So the diagram is showing us some outlet points and the labels of those outlet points. The very bottom outlet point is labeled X, and some one of the outlet point is labeled Y, and we have been asked to tell the name of the material that is exiting or coming out through this outlet points from this blast furnace. And these are molten iron or molten slag that comes out from these outlet points, from these X and Y points respectively. Things that come out are called molten iron and molten slag respectively. So this is the answer to this question. And the part 2, the same question is asking us, it is talking about the extraction of iron from its ore, because iron does not occur naturally in the pure form. It always is in the form of ore, and this ore is then refined to extract iron from it. So this is what this question is talking about, and this is done by some chemical treatment and some processes, which also involves heating the ore. For some ores, there may be some other processes, but now we are talking about the iron ore here, from which we extract iron. There are different ores uh, from which iron can be extracted, and but now in this question we have been asked to name one particular iron ore, and this is in the context of blast furnace. So which ore the treatment is involving the heating of the ore and in the presence of carbon in blast furnace. So In the context of blast furnace or inside the blast furnace, the ore that is being used to extract iron by some chemical treatment is hematite ore. So this is the ore. This is used to extract ore the blast furnace way. All right. Now the part three. This is a question which is talking about some geographical specification of naming some particular rock associated with the Bahamas, and also the name is named it as Bahamian rock. Okay, and this is asking us to name the chemical compound that can be found in that particular rock, and that is being also used in blast furnace. And this is calcium carbonate, CaCO3, calcium carbon oxygen combined to make this compound calcium carbonate. All right, and now we are moving towards subsection B. We have been presented with one equation. This is the reduction of iron, reduction of iron oxide through carbon monoxide to make the product of iron also carbon dioxide. And the question is asking us, this is the numerical question, and it is asking us about the mole of number of mole of iron that are produced this way. So this is on the left side of the equation is iron 3 oxide. This is treated with carbon monoxide to produce iron, and this iron 3 oxide is being reduced. So there are basically two processes. One is called reduction and the other is oxidation, and this is the process of reduction of iron 3 oxide to extract iron from it. And this treatment of iron 3 oxide is being done by carbon monoxide. So now we have been given with this equation, and we have been asked to find the number of moles that that are being produced this way, number of moles of iron. So we just put this, this plug in these numbers, and then we somehow calculate this to see that this is 223.38 grams. Okay, this is it. And then the part 2 says uh, mass of iron produced by answer. Yes, this is it. 223.38 grams. Okay, and then moving on to the next question. Uh, they have written about the extraction of gold and silver that were extracted in the olden days, and metals like sodium, calcium, and aluminum were extracted only recently. This is the case, and the question is about the reactivity of metals extracted in ancient times and metals extracted in recent times. So the answer to this is gold and silver are low in reactivity. This question is asking us about this reactivity of these elements, which were some of them were extracted in ancient times, and some of them are extracted only recently. So they have presented us the names of some of the extracted elements, and we have been asked to indicate about the reactivity of these metals. Gold and silver, which are the elements that also were being extracted in ancient times, they are low in reactivity. But sodium, calcium, and aluminum are high in reactivity. and this reactivity also plays a very important role in this process of extraction. Again, the same, somewhat same thing. Why metals like sodium, calcium, and aluminum are extracted recently? So now in this time and age, we have also the methodology of electrolysis, and this electrolysis has made things a lot easier in the context of extraction. So some of the extraction uh, can be done using this electrolysis as well. So the process of actual electrolysis is very useful in this context as well. Okay, iron and aluminum industry. Then we have this subsection D, iron and aluminum are industrially important metals. So why iron is so much being used in the construction industry? So one of the property that is being asked to us there, although there are many properties of iron, and there are many reasons why iron is being used in construction, for example. So one we can say, because this is only a one mark question, durability is something that also is in favor of iron to make it a good candidate to be used in the construction industry. Okay, and the part two is asking us about the property of aluminum that makes it useful in the manufacture of aircraft. So aluminum is a lightweight element, and if you want to make some flying object, it is a common sense thing to look at it like this: that if something is going to fly, it should have as much low a weight as possible and be strong at the same time. So aluminum, while not being only strong, is also very lightweight. So it is durable, it is not prone to corrosion, it is lightweight, it is strong. Okay, so it has a, I mean, a good combination of properties. So because this also is a one marker question, so one property I can write is like just lightweight. I can write about any of the good things about aluminum, which makes it a good candidate to be used in the aircraft industry and making airplanes and flying objects like this. Okay, now towards the fifth question, and now we have a question which says hydrogen is the most abundant element in the universe. Okay, free hydrogen is very rare on Earth, but compound containing hydrogen are common. Water is, yes, water is the most abundant compound. Of course, almost one third of this planet, but that we live in, is said to be occupied by water bodies or oceans, places that one, I mean, three-fourth of the place have is not land, right? It's occupied by water. So yes, it is one of the most abundant in this planet as well. All right. So hydrogen can be produced with electricity and water. Yes. Okay. Free hydrogen is rare. Yeah, but we have this abundance of water, and if we electrolyze the water, and we can separate the water into hydrogen and oxygen, and this way we are able to obtain free hydrogen, because free hydrogen does not occur in nature. I mean, if even if it does, it's very rare. Okay, so as a safe assumption, we can say that it doesn't occur in nature. Okay, but we have to undergo some process to obtain free hydrogen if you want, or if you have need to have it. So this is the scenario, and the question is also giving us an equation, and we have been asked to balance the equation. This is the equation which is the electrolysis of water. So this is H2O is water as a reactant, and then this arrow says this water is electrolyzed as separating hydrogen and oxygen, or we can say that water is being broken apart, or water is being broken into its building blocks, which are hydrogen and oxygen. So here we have the blank, and we have just have to balance it. So how do we balance an equation? We have to look at both sides of the equation, and which side is which. So we, as we see here, is the arrow. On the left side the arrow are always reactant, on the right side are always products. So we have to look on the left and right side of the arrow, and we have to make the number of atoms on either side equal. So this is how we do it. If we have H2 here, one uh, molecule of water, and if on the other side we have one molecule of hydrogen gas, okay, and one molecule of diatomic oxygen gas as well. So if we just leave it like this, here we have two atoms of hydrogen, on the other hand we have two atoms of hydrogen. This is okay, but we have one atom of hydrogen oxygen here. On the right side we have two atoms of oxygen. This is not balanced. So we have to balance it. We have to put in some numbers in the blanks that makes for hydrogen as well as for oxygen equal number of atoms on either side of the reaction. So if we put 2 here, we have 4 hydrogen atoms this way, because it's hydrogen. H2 means 2 atoms, and if we put a coefficient, so it means uh, 2 hydrogen molecules in total to 4 atoms. So if we also put 2 here, this also is 4 atom of hydrogen. Uh, if we put a coefficient here, this coefficient is not only for H but also for O. So this O becomes 2, and if you put 1 here, this O becomes 2. So hydrogen is 4 here and 4 here, oxygen is 2 here and 2 here. So this is now is balanced. This is how a balanced equation. So we have to equalize the number of atoms in a reaction to balance an equation. And this is telling us that this is a process whereby this much of heat is being supplied uh, for this process to occur. So this is 286 kilojoule per mole of heat required for this process to happen. Okay. And attaching here is a question which is asking us to state whether the reaction is endothermic or exothermic. Okay. So this reaction is endothermic because it absorbs, or it gets this much, or this much energy is being supplied to water to uh, form these products and get broken apart into hydrogen and oxygen. Okay, so this was the energy which is being supplied to water to get broken apart into its constituents. So because it accepts energy to get broken apart, this is an endothermic reaction. This reaction is an endothermic reaction because it accepts energy or heat. Okay. Part 3 is asking us to describe the test to identify hydrogen gas and give its possible results. So the test is that if we just take a candle, a burning candle, and if we have some suspected or prospective hydrogen source, and we want to confirm if it's like that, uh, what we what is whatever it is a prospective source, if it really has hydrogen or not, we just need to bring closer to it a burning candle. So we just have to observe if we have some popping sound, it means the hydrogen is getting burned from the flame of the candle. So it means there's hydrogen available there. That's why it's getting burned. In absence of hydrogen, it, it, it will not do the thing. I mean, if there is no hydrogen, there is nothing to get burned from the candle. But if there is hydrogen, only then we will have some popping mechanism or popping sound from the candle. It means that this flame of candle is burning the hydrogen, and we will be ascertain in our claim that this particular location is a hydrogen source or hydrogen is available there. So this is how we do it. We test, we do the pop. This is called a pop test. Just put a flame near to the source, and if we have some pop sound or pop mechanism undergoing there, then we will be sure that this there is the availability of hydrogen there, which is getting burned from this flame. Okay, this is a test, and same thing which I just said. The result is, because hydrogen is flammable. If you put a flame near to it, it will get burned because it is flammable, and and thus we get the pop sound when it burns. Okay. Now I check again how it is working. 48 minutes. Okay. Now we will move towards part B, and we say that it's hydrogen can be prepared in the laboratory, and this is a laboratory equation for the hydrogen for the preparation of hydrogen. Okay, as we can see here, one of the products is hydrogen gas. Okay, now at room temperature and pressure, we have been asked to figure out the number of moles in this much volume of hydrogen. Okay, so we have the famous formula, this one. This is a PV is equal to NRT formula. We have just modified it according to our requirement. We have to find the number of moles with a small n in there. So the condition is room temperature and pressure. This is the standard condition, and here pressure is 1 atmosphere. This is one here. V is 6 for 6,000 centimeter cube. We have just converted into liters. We can do this because we just remove this three zeros and it will be turned into liter this for the volume value, and we just put it here uh, because liter is a standard unit of calculation. And then we this is the universal gas constant. It has some uh, com- complicated unit form, but we don't need to worry about the exact magnitude of those units because the, all of those uh, units will get cancelled out in the calculation, and we just care about this numerical value 0.0821 for the universal gas constant. And then for the temperature, what we do is we just add to 273 to the temperature. We just assume the room temperature is 27 degrees celsius, and in 27 degrees celsius we'll just add 300 because we want to convert into the unit of Kelvin, which is the standard unit to do calculations. And just this is just what we have done here. Which is just manipulated, and we just see this is what we get, 6 over 24.63. And if we just do uh, further manipulation, we will just get this much moles. So this is roughly one fourth of the moles what we could have in this much of volume of hydrogen. Okay, this is the number of moles in this much volume of hydrogen. Now is the part C. It's asking us to name a process of ammonia production, and also is telling us that hydrogen is mostly in large quantities used to manufacture ammonia. We just need to name the process which is mostly in use to manufacture ammonia, which is Haber process. So what is the mechanism? Hydrogen reacts with nitrogen, and nitrogen is abundant in air in atmosphere. So if you recall, what are the constituents of ammonia? Is it they are nothing but hydrogen and nitrogen. So hydrogen is the one of the reactants, and nitrogen comes from the air. So it reacts with nitrogen from the air, and thus it forms ammonia. And the mechanism, I mean, this is a whole process that allows to react. Uh, I mean, allows hydrogen to react with nitrogen. This is a well thought out process, and it, under certain uh, a certain mechanism is being devised to allow hydrogen to do just that, and this is process is known as Haber process. Okay, and now we will move towards part D. We have been shown up with a diagram. Okay, hydrogen is passed over this copper 2 oxide until all of the copper 2 oxide changes to copper. So copper is just getting reduced here because oxygen is leaving copper. Okay, oxygen is leaving copper 2 oxide, and this copper 2 oxide is turning into copper. So this copper 2 oxide is in a in this glass object, we can say, in this lab apparatus, within this lab apparatus, and this is a point where unreacted hydrogen gas burnt off. Hydrogen gas is being supplied from here, and heat is supplied from here. This is the whole setup, and the equation related to this is this copper to oxide reacts with hydrogen and gets reduced. Hydrogen is working as a reducing agent here, and itself is getting it is getting oxidized, and copper to oxide is working as an oxidizing agent for hydrogen, and in turn it is getting reduced. So it is getting reduced into copper. So this is the process, and this is the equation, and from this equation it is asking us what is happening to the movement of electrons in copper atom in CuO. So because in copper to oxide, copper is one of the ions, the oxygen being the other. So while copper was in ionic form, it had plus 2 charge because oxygen is much more electronegative. So it attracts electrons, valence electrons from copper in order to form bond with copper. Okay. So what two electrons were um, which were given off by copper when copper became a positive 2 ion, they were regained. They were regained to make copper electrically neutral. When copper 2 oxide undergoes this process, and copper 2 oxide as a whole gets reduced, resulting in the formation of copper metal. This copper metal now has 2 electrons more than it had, uh, I mean, than its ion had when uh, its ion was a building block of copper 2 oxide. This copper ion in copper 2 oxide has 2 electrons less than this copper metal. So 2 electrons that were not with this copper ion, this copper ion regains 2 of those electrons and becomes copper metal. So this is what is happening with the electrons of copper here in this reaction. And the part 2 uh, also I think is yes, it is linked with this equation again, and the question is why this unreacted hydrogen is getting burnt, and the answer is this atmosphere or this air where this hydrogen is, it has a lot of oxygen, and oxygen reacts with hydrogen or hydrogen reacts with oxygen. So in doing so, if it reacts with oxygen, it has to undergo the process of burning. When hydrogen reacts with oxygen, it burns. So this is why even though this hydrogen does not uh, necessarily react with copper to oxide, still it's getting burned. Why? Because it is reacting with oxygen. When this hydrogen, which is unreacted, is reacting with oxygen but not with this copper 2 oxide, it will burn. And what will be the outcome of this burning? The outcome will be the formation of water. So as we all know that in water there are the presence of hydrogen and oxygen. So when this reaction of hydrogen and oxygen takes place, the result is the formation of water. And also this hydrogen gets burnt when it reacts with oxygen. Okay. Now we have to see what is in the subsection E. So here are some data, and we have been given with some values of some uh, things, and we have been given the grammage of apparatus, and we have been given with the grammage of the system when the apparatus has some copper dioxide, but it is before heating. Okay, definitely, if something has some mass before heating, it will reduce. This mass will reduce or decrease after heating, right? Because after heating some chemical, I mean during the process of heating some chemical process happens, evaporation and things like this, and the mass gets decreased of the substance that is being heated. So after this copper, I mean this compound gets heated. Okay, it turns into copper. Okay, and the mass of this copper on the same apparatus is now 4 grams less. So before heating it was only the mass minus the apparatus was 20 grams. Now we have to write the mass of copper after heating. So because the system mass before heating was 44.25 gram, and the system mass after heating is 40.25 grams, so this is a difference of 4. I mean, oh wait, this is the answer of the last one. Mass of copper after heating. Let me see. Mass of copper after heating. Uh, Mass of copper. So it is asking us only the mass of copper after heating, not the whole system mass, which included apparatus as well. So if we just exclude the mass of apparatus, which is 24.25, and we have to exclude it from this mass of the system. So this system which included the apparatus and copper after heating, we have to take this value which is 40.25, and we have to exclude from this the mass of apparatus which is 24.25. So if we exclude 24 to for 24.25 from 40.25, we are left with only with 16 grams. So this is what we have to write in here, only the mass of copper excluding the mass of apparatus. Okay, and then mass of oxygen removed. So if you see, the system mass before heating was 40. The system mass before heating was 44.25, and after 40.25 we have to take the difference between this. So this is a difference of only 4 grams. So it means that oxygen is removed when the process of heating is done. Okay, so how much of the removal? This is the removal of 4 grams when the process of heating happens. It removes oxygen, and this is of 4 grams. That's why we have this 44.25 decreased to 40.25 after heating. Okay, and now the next question is question number 6. This question is related to electroplating. Electroplating is a property of use is a commonly used technique to change surface property of metal plastic. Okay, surface property of metal plastic, and this technique improves the property of the original metal. Okay, This is the scenario, and the question is on the diagram, draw the electrode needed to electroplate a spoon of the silver. So what happens is there are two terminals or two electrodes, you can say, positive electrode and negative electrode. Negative electrode is called cathode because cations, which are positively charged ions, move towards it, and negative electrode is called anode because uh, positive end of the electrode is called anode because negatively charged anions move towards anode because opposite charges attract, like charges repel. So here in our case, we have to make spoon as a electrode, and this happens to be a negative side of the or negative electrode. Or negative electrode is cathode, so we call it spoon cathode. And silver because we have to electroplate, do the process of electroplating with silver. So the other electrode has to have a silver, uh, silver electrode. So this is a positive electron, a positive anode. So this is silver anode, Ag. Ag is the symbol for silver. And because the electroplating has to be done with silver, the electrolyte has to be a, has to be of some suitable compound for this process, it, which happens to be silver nitrate aqueous. Okay, so what we have to do is we have to label, we have to tell which is which. Okay, spoon is here, silver is here, this is cathode, this is anode. Cations will go this way, anions will go that way, and name the electrolyte. This is silver nitrate. Okay, and write the symbol for the anion is Ag plus, NO3 minus for nitrate ion. Okay, okay. Name the electrolyte at which the metal forms an ion. This is cathode. Then the electron reduction occurs at cathode industry. Okay, this one is a bit more detailed answer, even though it's only for 1 mark. So, but I thought to write a bit more of understanding. Yeah. So, chromium electroplating. This question is all about electroplating, and chromium is a metal which is also used as a material for to electroplate substances or stuff with. So, automotive industry. Yes, automotive industry is one of the industry which we have to tell an industry where electroplating using chromium is done, or and it's very useful there. So there is one good example is automotive industry because there are metal parts in a car, for example, or in a motorcycle or motorbike, which needs to have long-lasting uh, corrosion prevention, and chromium is the one good element to use here then for this purpose, and it also serves some other purposes which are of crucial importance in the automotive industry. uh, some of these are it looks good on the things that it gets electroplated on, and it is long lasting. Electroplating goes a long way, and it can also be done on stuff like plastic, and it gives a good shine to the stuff it gets electroplated on. Um Looks good, gives good reflection to the surface. Okay, these are some of the important things. Party. So sometimes plastic objects like trophies are made from plastic. I mean, quite a lot of times, and it also is uh, being done electroplated on. But before doing that, graphite is something that this plastic is coated with. So why, and I mean, why is graphite in the picture of? because we are electroplating with silver. Why do we have to coat the plastic thing with graphite before we electroplate the plastic object with silver? So this is because if we don't have graphite, we cannot use plastic as an electrode, because plastic itself is not conductive. So we have to make the electrode which we want to do electroplating on conductive. So graphite coating makes the surface conductive, and if it's conductive, then the cations will move towards the cathode, which is the plastic object in our case, which is coated with graphite. So graphite makes the surface conductive, and cations move towards it, and hence the process of electroplating gets done in the case of plastics. Okay, this is why graphite is of importance here. Okay, now move to the next question. Organic compounds, ethane, methane, propane. So we have to give one source of methane from where methane comes: wetlands, okay, swamps, agricultural land, these kind of places. One of the places from where methane can generate it. Okay, so this is the answer of part one of subsection A of question number 7. And now part two is asking us one commercial use. As a forklift fuel, we can use propane. Propane has its utility in working as a fuel for the forklift. One of the uses, we only have to mention one on of the common uses here. So this is one of those utilities of propane. And subsection B, part one is asking us a general form of homologous series and the above organic compound. Okay, so this ethane, methane, and propane, they all belong to the same homologous series, because they are all what uh, is referred to as alkane. They are part of the alkane series. Okay, homologous series is a series in which we have some specific increment in the number of carbon and hydrogen atoms as we move along the series. So as we move along the series in the forward direction, we have some increment in the number of carbon and hydrogen atoms. As you can see, the first member of this homologous series is methane. So methane has one carbon and four hydrogen atoms. The second one is ethane. Ethane is two carbon and four hydrogen atoms. So the increment from methane to ethane in the number of in the number of carbon atom is one, and the number of hydrogen atom is two. Okay, so we have moved one step in the forward direction in the homologous series when we move from methane to ethane, and further on we move from ethane to propane. We see a even more increase in the number of carbon atoms by one, and the number of increase in the hydrogen atoms by two. So this is the pattern. If we keep on moving from one member to the next in the series, we will have a change in the number of carbon and hydrogen atom. We will have an increase or decrease depending on the direction we are moving in the homologous series. So this is the homologous series, which is called alkane, of which ethane, methane, and propane all are members. And general formula for the alkane series is CnH2 and plus 2. So, for example, if we put N as 1 here, so this will become CH4. If you put N as 2, it will become C2H6. If you put C as 5, it will become C5H12. Okay, this is how it goes. All right, and then part 2, fourth member. Fourth member. Okay, fourth member is not pentane but butane. Best of my knowledge, it's butane, and then comes pentane. So it works like this: methane, ethane, propane, butane, pentane, hexane, heptane, octane, nonane, decane. This is the whole homologous series of alkane. Okay, and then we have to draw the structural formula for butane. Mistakenly, I have drawn here for pentane, uh, but for butane it will be only one C less here. Let me try to modify it if I can. So this H will not be here, but here, and this H will not be here. This line will not be here. This will not be here. Okay. So the basic idea is butane has to have four carbon atoms and 10 hydrogen atoms. So if you look up the formula, if you put 4 here for C4, H2 times H2 times 4 is H8 plus 2 10. So C4 is H10 is the formula for butane. When C is 4, H is 10 for butane. Okay, so this is it for the part 3, and then C section subsection C part 1 is asking us complete the work equation. So when methane gas is combined with bromine gas, what do we get? One of the reactants, one of the products is given, which is hydrogen bromide, and the other is missing, which is bromomethane. So when two are the reactants as follows: methane gas and bromine gas, they combine or they react together to form two products, which are bromomethane and hydrogen bromide. Right, then part 2. What happens to the color of bromine water when methane is reacted with the bromine water? Bromine has a characteristic yellow color. So when methane reacts with bromine water, it changes nothing. The color stays the same. Now part D, subsection D. So we have been given with an equation here. This is for wine. We have ethyl alcohol, and ethyl alcohol is put in open, and from oxygen in the open, it reacts it with, and as a result, it forms acetic acid or ethanoic acid and water. So we have to write the name of the reaction. This is oxidation, because ethyl alcohol is of interest for us here. Ethyl alcohol is a main reactant. This oxygen just comes from the air. So this is what it reacts with to form ethanoic acid and water, and this ethyl alcohol is getting oxidized to form acetic acid or ethanoic acid. This is oxidation reaction. Now question number 8. Many vehicles use petrol or gasoline as fuel for their engines. So yes, this is the case. And part subsection A, part 1 says, then the harmful metal is no longer added to gasoline. So the harmful metal that used to be the part of gasoline was lead, and it's not that much common now these days to have lead in the gasoline due to its harmful characteristics. Characteristics, it's not the part of gasoline anymore. So commonly it's not that much there. And then part 2 is effect of this metal has on developing infants. So mostly lead is responsible for affecting younger ones like children and infants, and where it attacks on their brain. So it has some it stimulates some malfunctioning of the brain uh, in younger ones. Okay, so it causes brain damage. Okay, and uh, uh, part 3 is we need to name an alternative for an unleaded petrol and diesel that is used in modern liquid petroleum gas, or LPG for short, is one of the commonly used alternative. Okay, complete the word equation for the combustion of an alkane. So combustion is when oxygen is reacted with something. So alkane is reacting with oxygen, and thus is get undergoing the process of combustion. As a result, is forming carbon dioxide and water vapor. Okay, so this is the completion of the reaction in terms of its products and reactants. And the second part is asking us when gasoline is combusted, insufficient oxygen, a poisonous gas is produced. Poisonous gas. So when there is no much enough oxygen available, and still, uh, but even with less oxygen, the combustion process can carry on. And when gasoline undergoes this process, it generates carbon monoxide. And carbon monoxide is a poisonous, a toxic gas. It's not that much friendly with health. Okay, so because there is a deficiency of oxygen, rather than CO2, we get only CO. No two atoms of oxygen with each atom of carbon. We only get one atom of oxygen with each atom of carbon because there is not that much oxygen available in some particular area in which the gasoline is getting combusted, and this carbon monoxide is poisonous that is being produced as a result there. Part 3. Okay, now it's asking us about the effect. So I mean, because this is not health friendly, it causes things like headache, dizziness, to name a few, and other things also uh, can um, can be seen in humans which are affected by carbon monoxide. Okay, I think this is the end of this paper 2, and in the next class we will see with some other exercise questions. Okay, till then, take care and bye.